Okay, so this is your assignment from Monday. And just to get started, you have to start off with what's your age on this one. So I'm gonna do mine because I'm 34. So 34, you start with your age on it. Okay, so you fill in whatever your age is. Obviously, none of y'all, I hope none of y'all are 34. If you're 34 and still a sophomore in high school, we need to have a talk. But I'm going to use my age just for the example. So based on this question, what would my known be for this problem?
34.
It would be 34 what? Rainbows, cats, pieces of broccoli? 34 what? 34 years, okay? So got to make sure your known always has numbers and units, okay? The units are equally as important, if almost not more important sometimes than the number, because the units are what guide how we do our plan and how we set up our problem, okay? So what is the unknown on here? What am I solving for on this question? So those of you who cannot hear, we had somebody in class that said it is seconds. And I can see it up here. It says, how old are you in seconds? Okay. So my plan always starts with the units of my known. So for this problem, it would start with years. Now my plan needs to end with the units of the unknown, which would be seconds, but there is not a good conversion factor that there's not one that'll go straight from years to seconds. Okay, I have to work with what I have up here, or maybe other conversion factors that I know. So looking at this, the only one that has years in it is the very first one. So I can go from years to days using that conversion factor. Then I could go from days to hours. I could go from hours to minutes, and then minutes to seconds. Now we did talk about last time, there was that shortcut where if you know how to go straight from hours to seconds, you can kind of skip the minute step. I didn't give you that conversion here on the box, but if you know it, then you can use that and it'll just shorten your plan by one step. But now when I go down here to set up the problem, I always start with my known, the number and the units. That goes in the top of my first box on my dimensional analysis setup for the chart. So I do not write anything underneath it. That box underneath it, it's blank. There's nothing down there, okay? So at this point, I have my known filled in. So now I need to look at my plan and I want to look and see, okay, my first step is to change years to days. So I need the conversion factor up here that involves years and days, which is this very first one, right at the top. So then my question becomes, do I write 1 year over 365 days? Or do I flip it the other way and do 365 days over 1 year? So, because I can flip it either way because they're equivalent. So which direction or which version do we need for the boxes down here? And how do I know which one is the correct one?
You flip it.
Which one?
The right one.
Sorry, somebody online said something. I couldn't hear him. Was that Gift? Was that you that said something?
Oh, I said flip it.
Oh, flip it. But flip which one?
Oh, the second one. It's gonna be like
Yeah.
365 days over 1 year.
Exactly. Okay. So, and that's what the people here in class said as well. So it is going to flip that way. And the reason it is because again, I look at my units up here that I started with for the known. That is your guide. The units are your guide. Okay. They're like your Sherpa in the dimensional analysis mountains. Okay. They're going to guide you through it. So because years is what I'm starting with, I have to put year down here so it cancels out. And that means the one goes down here and the other part of the conversion factor, which is my 365 days, goes on top. And so now I can show that the years properly cancel out because they're opposite diagonally. There's one on the top, one on the bottom. And then I can keep going. So from there, it's just kind of you repeat it until you finish your plan. So my next step would be to go days to hours. I'm going to use my next conversion factor up here, which this, yep, 24 hours in one day. And because I need to have day down here because I want to cancel day out. So one day will go down here, 24 hours will go on top. That way days cancels out. I'm not going to change color again. Back to purple, we'll just leave it red. And then my next step is hours to minutes. So I can use the 1 hour equals 60 minutes. And again, I would put hour down here so that it cancels. So the 1 hour goes down here and the, oh, I almost wrote 24 again. 60 minutes would go on top. So the hour cancels out with hour up here. And then my last step then, my plan up here is minutes to seconds. And so since I need minute down here to cancel, the 1 minute and that goes at the bottom, 60 seconds goes on top. That way minutes cancels out, okay? I know that I'm done because if I go back up here, I wanted to, my unknown was seconds, and I now have the unit of seconds on the top of my boxes on this last one. So when you get to the unit your unknown is, that's when you know you're done because everything else is canceled out, okay? So now it's just a matter of doing the math in your calculator. On this problem, all of our numbers are on top. On the bottom, they're all ones down here. And while technically, yes, we are going to be dividing by 1 4 times, dividing by 1 does not change the value of our answer. So in our calculator, we really just need to multiply all the numbers across the top on this one. And then you would get your answer from that. I'm assuming it's probably gonna be a very, very large number, okay, because everything's being multiplied, okay? Now, on your other ones, just to kind of go over this kind of the basic, like how to get to the known and stuff like that, if you were not able to like find something that you can chew and time yourself at home, I did a little like gummy fruit thing here at school on Monday, and I told you guys, I don't know if I said it on Remind or Canvas, but my little thing was about 2 grams, and it took me, I believe it was 11 seconds that I said to chew it. So that's my mass and my time. And so I'm going to write it as a conversion factor. 2 grams equals 11 seconds because that's what I measure. That's how long it took me. And then I'm just going to write it down here again in my box with my other conversion factors. And so looking at this question for number 2, what do you guys think the known is on this question? Nope, that's a conversion factor. That can't be my known. Yep, my known is 1 kilogram. So the known is always going to be the number with units that's in the question. Okay. So my known is 1 kilogram. What is my unknown on this question? Minutes, okay, because it's just units. It says how many, so question mark minutes, okay? So my plan starts with kilograms, and then I'm gonna set up my plan. My plan needs to end with minutes, okay? But up here in this box, these are my conversion factors that I have to work with. So what can I change kilograms to first? Grams, because this first conversion factor connects kilograms to grams. After I change to grams, then what can I change grams to? I can go to seconds. That's where your measurement comes in. This one, I meant to do the highlighter. This one right here that we measured, we made that a conversion factor so we could use it to change from grams to seconds. And then seconds to minutes with my other time conversion factor. So that's my plan. So when you go to set it up, follow that plan. And then I also gave you kind of a hint down here at the bottom. Now, you are showing your work here in these boxes. That's where you should be typing or writing. So if you're typing on Google Docs, you could type in those boxes. If you have the ability to write like I'm writing, because you have some sort of app or PDF thing that you can write on, feel free to do that. There are things that exist that let you do that. But I gave you a hint down here for like the guide for the units. So you'll be starting with the 1 kilogram, and then you'll follow your units to set up your other conversion factors like this. But your work again should be up here in the boxes. Now, I will tell you on that first one, it was all multiplication. On these other ones, you're going to have some multiplication, some division. You might have to do both in one problem. It's fine. Just multiply the numbers on top and then divide by the numbers on the bottom. Okay, as long as you do that, you're going to get the right answer. The walking one, on this one, you had to record how long it took you to walk 10 meters. I did, somebody was like, they didn't know how to measure it, or they didn't have a way to measure it. So I got somebody else's info. So if you need a number, somebody told me it took them 9 seconds to walk 10 meters. Well, somebody else said 9 too. So that must be an average or like a good number. Hold on, I'm trying to reconnect, guys.
Give me this thing, like chassis wheel. It's a base for the fence. I think because it's a they measure something in my way. Like it's something.
All right, so for today's lesson, we're going to talk about kind of the intro to the mole and like what the mole is in chemistry. So in chemistry, when you hear the word mole, it's a unit of measurement. And so it's a way that we group together very large amounts of things. Typically, we use it for atoms and molecules because atoms and molecules are very, very small. And because of that, we can't see them. They're hard to do, you know, it's not like we can calculate and measure out, you know, 2 atoms here in the lab, okay? So what they did is that chemists came up with this concept of a mole as sort of a way to like bundle together atoms and molecules and make them easier to actually do calculations with or actually work with in a lab setting, and to do things with when we would actually be interacting with them rather than only working with like 3 atoms, which is basically impossible, okay? And so just like here it says, if you hear the word or the term 1 dozen, usually you think of 12, like a dozen eggs. That's how you buy eggs at the store. You don't buy 1 egg, you buy a dozen eggs, okay? Which is 12. So in chemistry, anytime you hear the word mole, we think of this number, this many items. And this number is called Avogadro's number. It's named after one of the scientists who did some of the initial kind of experimentation and research to kind of come up with the concept of this number for molecules and atoms. And there's a video at the end of the notes that has a little bit more information about him and about the number and all that kind of stuff. But basically, if we were to write out the number expanded, this is what it would look like. It's a really large number. It's raised to the 23rd power, so that means there's 23 zeros after the 6, okay? And so we can use the word mole to describe other non-chemistry items. So like if I had a mole of cars, I could have, you know, 602 sectillion. That's how I would read that number. It's 602 sectillion, okay? Okay, so we can use it to measure other like non-chemistry things like on this table, but like we don't really, because like nobody needs a mole of elephants or a mole of cats. Like nobody needs that many. For small things like grains of sand, grains of rice, it would maybe make a little bit more sense if I had a mole of rice. I would have 602 sectillion grains of rice, because grains of rice are really small to count, just like grains of sand. And so Avogadro's number is going to be one of the conversion factors that we are going to use in this unit and you know later on in this semester to do calculations, because we are going to be converting between moles and particles, because particles are too small, we can't really do anything with them. And so we're going to convert between moles and particles. And then our second thing we're going to talk about today is that we can also convert between moles and mass in grams. And so we use the fact that we know 1 mole of any chemical substance, whether it's an element or a compound or anything, equals this many particles of that substance. Now the particles, there's 3 main terms that we can use for particles that are specific. Particles is like generic, and atoms are used for single elements. So if you're getting an element from the periodic table that is not one of the diatomic elements, then those are measured with atoms, okay? So like aluminum, sulfur, iron, most of the periodic table, except for our 7 diatomic elements. The diatomic elements, as well as our covalent compounds where we have all the nonmetals bonded, like carbon dioxide and water, those compounds where all you have are nonmetals are measured in molecules, okay? So if you have a diatomic element or a covalent / molecular compound where you have two nonmetals, those are molecules. The third one is one that we probably have never heard before, and it's called formula units. It's specifically used only for ionic compounds. So things where you have like a metal and a nonmetal, or maybe like a metal and a polyatomic ion, like these. So sodium chloride or potassium nitrate. And the reason that these don't exist, that these give formula units, is because ionic compounds where we have the positive and then the negative ions, they don't exist in molecules. They exist in these kind of structures where you have positive and negative ions alternating. And so we call them formula units because you have a unit of that ionic compound. There's no discrete molecules like with our covalent compounds or the diatomic elements. So just know that if you see atoms, molecules, or formula units, all of those are particles. So all of those are probably going to mean that you're going to need to use Avogadro's number in your calculation. Okay. Now this number 6.02 times 10 to the 23rd. This number is written in what we call scientific notation. So I'm going to switch over here and we're going to do just a quick recap, because scientific notation is technically something that you are supposed to learn in your 8th grade math class. So this should not be brand new information to you. It should just hopefully be somewhat of a refresher. But the purpose of scientific notation is it's a way to write numbers that allows us to write really small or really big numbers in a way that's easier for us to read and easier for us to use for calculations. So you use this a lot in science classes because, you know, things like atoms, molecules, cells in your biology classes, they're really small. So if you're talking about like the size, like to measure them, it's going to be some number that's raised probably to a negative exponent because they're very small. But if you're talking about large quantities, like with our mole, that's a really large amount of a substance. It's to the positive 23rd power. Or if you're in like physics or astronomy and you're measuring like the distances between planets, then those are going to be large numbers. And so we use scientific notation because a lot of the values that we use in science classes tend to be really small or really large, depending on what you're dealing with. So when we write it, you're going to have, you're going to write the numbers of your digits, but you'll have a decimal point after the first digit. There's only one digit to the left of the decimal point, okay? So it means it can't be bigger than like 9 point something or smaller than 1 point something. Then you'll have a times 10, and the 10 will be raised to a power. The power or that exponent, that number represents how many places you had to move the decimal to change the number into scientific notation. So for example, if I have this number, these two numbers, these are the same value. This one is written in standard notation, just like a regular number. This one is written in scientific notation, but they have the same value. They're the same amount. They're just written 2 different ways, okay? And so what happens is in this 50,500, the decimal is here at the end, and I would have to move it 1, 2, 3, 4 times in order to only have 1 digit to the left. And so it becomes 5.05 times 10. And because I moved it 4 times, it's a 4 here. One digit to the left, yes. Yes. Yeah, and we're going to look at a couple more examples. So how you would do this if you're trying to change number into scientific notation, you want to move your decimal so there's only 1 digit to the left or in front of it, okay? Then you rewrite it as the number with the decimal, then you add the times 10 after that, and then you put your exponent after the 10, and the exponent represents the number of places you moved the decimal. So exponents can be positive or negative. On that example we just looked at, the example was positive because the number was very large. So your exponent will be positive if you start with a big number. So anything greater than 1, okay? If you have a small number that's a decimal, like 0.00083 or something like that, that's going to give you a negative exponent because that means the number you started with was very small. It was less than 1. So it was some small, tiny decimal number. And so we're going to look at a couple more examples of how to sort of move and change the numbers into scientific notation. And then we're going to take a look at a couple where we're going to go backwards. They're going to give us scientific notation and we have to change it to the standard notation, like a regular number. Okay, so here's this number, 101,000. It says convert it into scientific notation. So how would I go about doing this? I would first figure out where is the decimal. Well, in a large number like this, where it's a large whole number, even though it's not printed, it's understood that the decimal is at the end of the number. Okay, so if you have a large whole number like this, the decimal is going to be at the end. Now, the question is, where do we want the decimal to be for our scientific notation to be written correctly? So here's where we want it to be. Okay, so now I would rewrite it. It would be 1.01. All the zeros at the end just drop off. We don't care about them. So 1.01. And then how many times did we move the decimal to make that happen? 1, 2, 3, 4, 5. So times 10, and it's a positive 5 because we moved 5 places, and it's positive because this number we started with was a very large number, 101,000. That's pretty big. It's definitely bigger than 1. So, and if you guys don't catch something, you can go rewatch it later because I'll upload this at the end of the day. And then that's how it would be written finally in scientific notation. 1.01 times 10 to the 5th power. On that one we did because there was a 1 in the number. So it was because it was 101. If it had been 100,000, if it was all zeros, we would have just done 1 times 10 to the 5th. Okay, so here's the second one. So now this one, first thing we need to figure out is, okay, where is the decimal and where do we want the decimal to be? So this one has the decimal printed, so we can see that pretty clearly. Where do we want the decimal to be at the end? Okay, I heard on the very right, and I heard between 9 and 8. Anybody online have an opinion? All right, that is correct. Because we want, if we move it all the way past the 8, there's gonna be 2 digits on the left, the 9 and the 8. We only want 1 digit on the left. So how many times do I need to move it to make that happen?
3 times.
3 times. Good job, Gift. So I'm going to rewrite it 9.8 because that's where my decimal's moving to. And then it's going to be times 10, and we're moving it 3 times, but it's a -3, not a +3. The reason it's a -3 is because we did move 3 places, but look at this number we started with. It was less than 1. It was a very small decimal number. So that's why it has a -3, because the negative tells me my number is small. Positive exponents mean big numbers. Negative exponents mean little numbers. Yes, but I don't want you to think that, because then when you change out of scientific notation, you do it wrong. So you can, if you can keep them straight, you can do that. You can do right and left, as long as you remember that going into scientific notation is one way and going out is the opposite way. We're about to see on the next one. Okay, so now we're going to backwards. This number's in scientific notation. We want to put it in standard notation, like a regular number. Yes. Okay, so this number 2.057 times 10 to the 2nd power is already in scientific notation. So if they ask us to convert to standard notation, that just means take it out of scientific notation and make it a regular number, like we would normally write it. Okay. So here's my number. So I want to look at the exponent. Always look at your exponent. That's going to tell you what you need to do. So because it's a 2, that means we're going to move the decimal 2 times. Because it's a +2, that means that our number is going to get bigger, which means that we would need to move our decimal to the right 2 places. And our number is 205.7. So here in class, Jose was kind of saying, you know, when you were converting the number into scientific notation, you could move the decimal, you know, left or right, and based on, you know, if it needed to be positive or negative exponent. You can think of the whole left and right thing. Just be aware that, you know, like this one, we had to move it to the right to take it out of scientific notation. But if you're trying to take a number into scientific notation, you move to the right, your exponent's negative. So it's If you can keep them straight, then you can remember it that way. But I would just, be careful because I don't want you guys to mix them up. Because, if I move to the right, changing to standard notation, it's a large number like this with a positive exponent. If I move to the right to change it into scientific notation, that means it was going to be a negative exponent because it was a small number to start with. Okay, so now here's another one, and it's in scientific notation, and they want us to change it or convert it to standard notation again. So here's my number. So how many times do we need to move the decimal, and which direction do we need to move it?
We move it 4 times to the left.
Okay, 4 times is correct because that's our exponent. And then it's negative, so that means our number is going to be a small number. So that means we will have to move it to the left. So what happens in this situation is I'm going to move it 1 time because it's going to go in front of the 3, but then there's no other number. So then what do I do? Well, you just keep going. We got to go 3 more times to move 4 places. And then here's my decimal now that I've moved it. So I got to fill in all those empty spots with zeros. And so my number is 0.00031. Because it's to the negative 4th power. So if I took this, if I converted it back, I would move it 1, 2, 3. I'd move it 4 times. And because it was a small number, it'd be 3.1 times 10 to the negative 4. So you really just need to be able to recognize these numbers, change numbers in and out. And then as we start getting into our calculations the next couple classes, we're going to talk about how you type these numbers into the calculator and actually do math with them, because there's a specific button on calculators that you have to use to type in scientific notation. You don't actually type like a times 10. There's a specific button you use that takes the place of the multiplication sign and the 10. Okay. And sometimes it's in different places on different calculators. So I'm gonna kind of show you the one that I have in class if you want to get one of those. And we'll look at where it is on the Google calculator and on the other scientific one that I have on Canvas. So we'll kind of cover all of them so that hopefully no matter what you use, you'll be able to type them in correctly. Because a lot of times what happens is we get to stuff like this and it's not, and like people will have their work on the paper all set up correctly, but because they don't know how to type it into the calculator correctly, they get the wrong answer. All right, so I'm gonna switch back to our. Okay, so the second part of the mole concept is I told you we can relate it to the molecules, the atoms, but nobody wants to count that many like atoms, and it's actually like physically impossible. Like there's no way for us to count that many of anything, but especially something as small as atoms and molecules that we can't even see. And so what they did was they did experimentation with gases and things, and they figured out, sort of equivalent volumes and masses that have this number of particles in them. And so we don't count Avogadro's number. When we do labs and we measure things, we measure masses of solid substances, or if they're gases, sometimes we'll measure their volume in liters, okay? So masses are also going to be used in this unit as a conversion factor. But the thing is, the mass is going to be different, because if I have a dozen ping pong balls, that's 12 ping pong balls. If I have a dozen golf balls, that's 12 golf balls. So I have the same number of items, but is the mass of 12 ping pong balls going to be the same as the mass of 12 golf balls? No, the golf balls are a lot heavier. They have a lot more mass in them. So just because you have the same number of items does not mean they weigh the same, okay? And so that's where this molar mass concept comes in. It's the mass of 1 mole of a substance. So for example, if I have the element carbon, 1 mole of carbon has Avogadro's number of atoms of carbon, and the mass or the weight of it is 12.01 grams. That's what's printed on the periodic table for carbon. It's atomic mass, okay? Except instead of atomic mass units, we're now going to measure it in grams. So we don't count out this many carbon atoms. We just weigh out 12.01 grams of carbon on a balance, and we say, oh, okay, that's 1 mole, so that's got 6.02 times 10 to the 23rd atoms of carbon in it, okay? So you'll be using your periodic table because you'll have to look up the masses of elements, okay? So some periodic tables, it's called atomic weight or atomic mass, okay? But it's usually at the bottom. It's the one with the decimals. So for example, hydrogen is 1.008. That's its atomic weight. Well, we're also going to use that for the molar mass. So 1 mole of any substance is equal to its molar mass in grams. So for example, hydrogen, 1 mole of hydrogen atoms would be 1.008 grams of hydrogen, okay? If I go back up here to carbon, 1 mole of carbon equals 12.01 grams of carbon, okay? And I can calculate this for compounds as well, where I have multiple elements. It just requires a little bit of multiplication and addition. We're not going to get into that today. That's going to come our next couple classes. For today, we're focused on just sort of the element side of it, okay? But you use your chemical formulas with your subscripts. You use that to help calculate the mass of like a compound, okay? And so the last part on here, which I'm not going to watch it here on the live call, but there's just a short, like 3-4 minute video here where it talks about the mole and sort of a little bit about the history of it and the development and like, why did they use the mole? How did they come up with it with Avogadro's number and all that stuff? And sort of how big the mole is, because it's really hard, you know, to wrap our minds around like a number that large, because it's 602 sectillion. That's more than like a billion, more than a trillion, you know, it's way more than that. In fact, one of the things they say in this video is that, I'm trying to remember exactly how it's worded, but they say if you were given a check on the day of your birth for a mole of pennies, so 6.02 times 10 to the 23rd pennies, not dollars, pennies, and you spent $1 million a second every day until you died at the age of, it's like 75 or 85, I can't remember the age in the video, but certain age, it's like really old, you would still have like 99% of your money in the bank. That's how big this number is. Yep. So, and you can watch it, it's real short, but you can watch it later, and it has more deals. It talks about like, if you had a mole of donuts, what you could do with that, and a mole of basketballs, what you could do with that. There's a couple of other things in there. But what I want to take the last little bit here of time to do today is to look at our assignment. Let me stop sharing. Oop, the bell's ringing. Okay, so when you go to the next page after your notes, you have a link to this assignment. You'll make a copy of it in Google Drive as a Google Doc, and you'll type your name, type your period, and then there are instructions on here. You're going to use an online simulation to help you answer this. And so this is a website we have not used yet, but we are going to be using it kind of throughout this semester now that we have access to it. So there's a direct link here. If you click this link, it will open it up in another tab. If that link for some reason doesn't work, or if you get an error that's like, it won't let you log in or whatever the case is, then no, I don't think so. If you get something that's like, it won't let you open it or whatever, then what you can do is you can actually access it through Rapid Identity. When you log into Rapid Identity, yours may not look exactly like this because I probably have a lot more things than you guys do since I'm a teacher, but you have your Canvas icon usually. And then down here, if you look, you'll find this blue with the G. That's the app that we're using right now. It's called Gizmos. And so you can access it. If you can't, the link doesn't work, you can go through Gizmos and you'll just look for the one that has to do with moles, okay? But this is what it looks like. If you click the link, it has moles. There's 3 tabs at the top. You're going to only be dealing with the first 2 for today, Avogadro's constant and conversions. And then when you look at your instructions, it's going to walk you through exactly what to do. It's going to tell you to like click this drop down menu and pick something else, and it'll tell you to like click and like I'm going to add some atoms, okay? So I'm adding some copper. Right now, my scoop is really small, so I'm not adding very many atoms, but I can, click here and I can drag, change my exponent. and I can add more atoms at one time. And so this is what we would see in the lab because we would be measuring grams on like a balance. This here in this box, this is the nanoscale view. So this is like if we had the ability to zoom in and look at the atoms and the molecules, this is what you would be seeing. Okay. And so you're going to go through, you'll go through your instructions. It'll walk you through exactly what to do. You're going to type in information in some areas. There's questions to answer. There's data tables. You'll type in information in. There are questions you'll answer. There's observations that you'll type in on different sections. And then this activity 2, you'll go to the second tab for conversions. And so here is a place where it's going to help you figure out the number of atoms. Over here, it's going to help you add mass, and you can kind of see the relationship between the particles or the atoms and the mass of a substance. And again, there's some different things you can change, like you can do different substances. So make sure you're reading your instructions so that you do the correct one. Okay. And so here's on your instructions, you can see like it says activity 1, Avogadro's constant tab, and here's the little image. Tells you to select copper. In the nanoscale view, put the copper atom on the scale and then record the weight on your data table down here. Try to match the weight with the scale on the right side. If needed, make the scoop larger by moving the exponent bar to the right. Once you've matched the weight, record the number of atoms that you have, okay? And then you're gonna repeat for one of the compounds, copper 1 oxide. And then it also has observations, so you can type in observations that you see or that you make while you're doing that. And then there are some questions to answer at the end. And then activity 2, you'll switch over to that second tab, like I said. And again, follow the instructions. So it tells you to select carbon, hit the start button, pour the jar to the left to count the number of atoms, record your results in the table, pour the same jar into the balance, record the results in the table. You'll repeat it for the other elements and compounds listed on the table, okay? And then again, questions to answer, there's boxes to type. And then you'll need a periodic table. It's got a link here, or if you need to look up one, you can. And then again, you just kind of keep going and then get down to your last question. So it should guide you through along with using that simulation. So again, if the link in here for some reason it doesn't log you in, go through Rapid Identity, because sometimes you need to be logged into, not sometimes, you do need to be logged into Rapid Identity to get it to work. Okay. All right. Any